longitudinal motion. This is bending motions. And the bending motions, you can see that how can you solve it? I'm going to quickly just run through this. How can you solve a PDE? We normally use we call assumed mode solutions. This is a Q and this is a phi here. All right. This phi is exactly the same as the transfer function matrix I introduced just last hour. This. Now, I have phi here. I have Q. Q is your monopoints. Q, this is your monopoints. And this is your transformation matrix. So W is equal to phi Q, and phi is only x dependent, and Q is only time dependent. So you separate in time and space. If you do set this into here, then you will find out your frequencies is just like this. This is exactly the same like you are doing transformation from your physical Hornet to the model Hornet. Your Q is really your model Hornet. This is the way you solve PDE. So solving PDE is very similar to you to solve the model Hornet transformation. Because if you do this, then you will be able to find that one equation that's this part only the x dependent, and this part is only time dependent. If these two will be equal, they have to be a constant. This only time dependent, this only the x dependent. Then you cannot have a time dependent equal to the x dependent unless these two equal to constant, and that constant happen to be your frequencies. That's the explanation of this. So if that's true, then you will be able to find two equations. One is only x dependent. One is only t dependent. The x dependent this, and the t dependent this. There are two equations. They are separate, and they are independent. They are not coupled together, because that's again phi, again q there. This is a way to solve PDE, partial differential equations. And from this, you will be able, from phi, you will be able to solve your shapes, your mode shapes. And if you look at this is very simple two form. And this is the power 4, and it's power 2. And if you do this, then the power 4 here, this is, if this is constant, and your solution will be C1, C2, C3, C4, and all exponential I beta 4, beta x minus beta x. And because of these properties, and then the real solution will be C1 sine beta x plus C2 cosine beta x plus C3 sine sinh beta x and C4 cosine beta x. And this is complex, and this is all real. Again, this solution has to be real solution. There's no complex. The complex solution doesn't do any good. You have to come back to real solutions. And this is real solution. And this is the mode shapes. And this is the shape. You will be able to see it. All right. And this just gives you some figure about the sinh and cosine, how they what kind of curve you will get, cosine and sinh. And this is nothing but the exponential functions. And that's just some definition of functions. And then this is the hyperbolic cosine and sinh. I'm not going to show you much about this. because this is some interesting animations for your hyperbolic equations. I'm going to skip this, okay? Then this is the way to solve your shapes. We call free boundary condition. At this end, at the root, your phi equal to 0 and your slope equal to 0. So x equal to 0 equals 0, dx d phi x dx equal to 0. That's this end, the displacement and the slope equal to 0. That's why you got this. And at this end, the moment, there's no moment. So d squared phi over dx squared equal to 0, and there's no shear force. So d cubed phi and dx cubed equal to 0. And this is vibration, this is not control. So, but I'm going to show you, because we might be able to, we might have to use some of those ideals, the mathematical ideals here, to solve a control problem. But anyway, this is the way to solve it, and I'm not going to spend too much time here, and because this equation, the bottom equation, allows you to solve the frequencies. This is just that, right? So your frequency equation, that's your frequency equations in the right hand side. And the frequency equation is boundary condition dependent. So you have a different boundary condition, you have a different frequency equations. And that frequency equation allows you to get the natural frequencies. Okay, that's if you plot it, your natural frequency, this first natural frequency, second natural frequency, third natural frequencies, and this allows you to solve the frequencies. And I think if you take vibration class, then they will talk about this more than I will do here. And so, the frequencies, look at this, omega 1, omega 2, omega 3. Omega 1, there's a constant square root of EI divided by rho L4. So frequency is EI dependent, is also rho dependent, and L4. And this is like a K over N. So square root K over N will be frequencies. And this is just like a square root K over N. And this is related to like an N. And there's some constant value here because this is constant value you will get from there. And this is some constant value get from there. It's d beta 1L. And so that's at here is the some constant value to look at. All right, I'm going to quickly, because we have other subject we need to talk about today. So there's some orthogonality property. So this is phi j, phi k, the mode shape j and mode shape k, they are orthogonal if j is not equal to k. All right, and this is exactly the same as your transformation matrix I showed you just a little while ago. Did you remember that? This square root over 2, and that's my phi here equal to 1 minus 1, right? And the transformation matrix. Remember that one? If you write this, then this will be equal to 1, 1, 0, 0. All right? That means this and that, the first column and second column, they are orthogonal. This. So that column and that column, this is the first column, this is first mode shape, and this is the second mode shape, and these two mode shapes are orthogonal. They are orthogonal because this one, that's 1 transpose times 1 minus 1, and you have square root 2, that's So this equal 0. That means these two columns are orthogonal. And this first column, first mode shape, the second column, second mode shape, is exact the same idea as you are seeing here. Phi j and phi k, they are orthogonal. But in this case, you have to integrate from 0 to L, then that's equal to 0. And so, unless j equal to k, they are all orthogonal. They are all orthogonal. The first mode and second mode, they are orthogonal. And the first mode, third mode, they are orthogonal. The second mode and third mode, they are orthogonal, and so on. It's an orthogonality property. It's a natural mode shape, and this is exactly the same as in the metric sense. So I'm showing you the monocoordinate transformation. If you remember that, the cap phi there, and they are orthogonal. So that's what orthogonal means. Alright? So, this is the mode shapes. If you look at this, the blue line is the first mode. Just like my first column, 1, 1. If you look at this first mode, they are all the same in the same directions. All the x, they're all going down or all going up. The second mode, if you look carefully here, the second mode is going down and then up. And there's one, if you look at this, at 0 line there, if you look at 0 line there, there's one cross section for the second mode. This is the green color. Green color, one down and going up. So, they are not all the same sign and all the x. The third mode, the red color, is now